C, no. C, no. CPE, no. C, yeah, CPU.
It would be nice to write a code to solve word search puzzles. Today's problem is about that, and it is called Word Search 2. It's been mostly asked by companies like Amazon, Microsoft, and Uber. Now, here is the question.
The question says, given an MN board of characters and a list of strings, which is called words, return all words on the board. So we have MN board, which is a 2D array, and the visual shape is something like this. And we also have an array of strings, which is called words. We have to return all the words that can be built by the characters in the board array. Then it says each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. And also the same letter cell may not be used more than once in the word. So it means that we can build words with these characters that we have horizontally or vertically, and also a mix of them. So, for example, as you can see, I can build the word oath by a mix of horizontal and vertical characters. So this is also accepted, but we cannot build words diagonally. Okay? And we have also some constraints. M equals to the length of the board, and N equals to board I lengths. In other words, M is the size of columns, and N is the size of rows on the to the array that we have. It also gave us the range of M and N, and it says that board IJ is a lowercase English letter, and it also gave us the length of each string in this array. So words I are also consist of lowercase English letters, and all the strings of words are unique, so we don't have duplicate words in the words array. Alright, let's talk about this example that we have here. So the words array consists of oath, pea, eat, and rain. We have already found oath, so it is one of the words in the output. And let's see, can we build or find P in this word or not? So as you can see, we don't have any P letter, so yeah, we cannot build that, so it's omitted. What about eat? Yeah, we can also build eat here, but we have to read it from right to left. So right to left iteration is also accepted by the question. And so this is check, and this is check. And what about rain? We have R here, but no A, no vertical or horizontal A, so also rain is not accepted. So the words that we can find or build with the characters that are given on the board are eat and oath. Now that we understood the question, let's talk about the suitable solution and algorithm. To understand the solution of this problem, let's see it with an example. So consider this is the 2D board that we have, to the array that we have, and this is the words array. In order to solve this problem, we need a data structure that is called trie. Trie is like a tree, but it begins with prefixes. So let's draw the trie of these strings that we have. This is the root, and we don't assign any character of these words to the root. Then we start each node based on the starting of these words. So we have O and D. So the first level nodes would be O and D. Then we have word oath. So we have O, A, T, and H. And we have dig. So we have I and G. Then we have dog. So we have again O, G, and also as we have dogs, we add an S to the end of it. The benefits of using this data structure are fast insertion, fast deletion, and most importantly, fast search. We can search in this data structure with O of the string length. And that's because we make it based on the common prefixes. So, for example, if we had word oat in the list, we would not make a new branch for oath. We just add H to T, so we can make word oath. To solve this problem, we start from the root of this trie. So we have O and D. So we have to look for O and D on the board. First, we look for O on the board. Thankfully, the first cell of the board is O, so we start from here. Keep in mind that we just search horizontal and vertical on the board, and we also do not backtrack to the cell that we have just seen, because the question says that we have to use each character on the board just once. So we start from here. The next character that we are looking for is A. So as you can see, O's neighbors are A and E. So as we are looking for A, we go this way. And we are here on the board. The next character that we are looking for is T. So we search for T. We have A here and T here. So we go this way. And the index is here. The next character that we are looking for is H. So we search for H on T's neighbors. We have E, A, and H here. So we go this way. And as you can see, we have found word oath on the board. So it's a mix of horizontal and vertical, and we are here. To optimize this solution more, we save the word that we have found on the last node. So as we have found oath on this node, oath, as we have found it here, we save it here. And it helps us in the future. So consider if we have another word, for example, author. If we save oath here, we don't have to start from the beginning to search for author, because author and oath have the same prefixes. So we just can start from H and go through other characters. Okay, now we have to start from the beginning, from the root of the trie again, to look for other words that we have. So we just found oath. So we start from the root again, and we are looking for D. So we search for D from the beginning of the board, and until we find D, other characters are not important for us. So we have A, N, E, A, E, T, and D. So we start from here. And D has two children, I and E. So we have to search for I and D on these neighbors on the board. We have A, O, and L. So we don't have any I, so dig cannot be found in this word. But as we have O, we go this way on the board. And we also move the indexes. Then we have to search for G. So as you can see, we have G here. So we go this way. And also move the indexes. So we have found word dog also on the board. So check. And then we have to look for dogs. So after G, I forgot to save the word. So again, we save the dog here on the G. So as you can see here, because we have saved dog on node G, we do not have to start from the beginning to search for dogs. We just start from node G and look for S. So on G's neighbors, we don't have any S, so that means we cannot find dogs also on the board. So the output would be oath and dog. Now that we understood the suitable solution to this problem, let's see how should we implement this algorithm. First, we have to implement the trinode class. As you can see, trinode is a hash map of character to trinode, because as you remember on the algorithm section, each node of the trie contained a character. We also declared a string which is called word, for each node of the try node to save the words that we find on each node. On the solution, we first declared the 2D board that we have, and the results array list that we have to return. We also have two methods here, find words and backtracking. Find words is a list type method, and it takes two parameters, the 2D board and the words string. Let's take a look at find words now. Find words contains two sections, building the try and backtracking. So let's see how should we build the try. First of all, I made a root, which is a try node, and then in a nested for loop, I built the try. In this for loop, I loop over each word of the words string. So for example, first I see oath and dig and so on. Then I assign the index to the root. Let me to draw it here so you can have a better understanding. First, we made the root of the try. This is a root that we have. And then we assign the root to the node. The node is the index that we had on the algorithm section. So first of all, the index is on the root. In the second loop, we loop over each letter of the word that we are tracing from the words string. First, we check if the current node's children contains the current letter of the word that we are looking at. So if it's true, then we move the index to the node that contains the letter. For example, here, if the children of this root contains O, we could move the index to this node. But as it's at the beginning of making the try, so the try is empty, so this condition is not true. In the else, we make a new node. So as it's empty, I make just a new node. And then we assign the current letter to the children of the current node, which is the root. So if the current letter is O, I assign O to this node. And we also move the index to this new node. So the index would be here for the next iteration. So this is a process of building the try. So at the end, we reach to something like this. And keep in mind, when we build a try for a word in the words list, for example, oath, we also assign the word to the word part of that node. And it's different from what I said on the algorithm section, because on the algorithm section, I said that whenever we find a word in the board, we just save it to the last node. But I made a mistake. Actually, the true way is that when we are building the try, and when a word is completed, like here, when I'm building the try and the word oath has been built in the try, I just save the oath on the last node, as you can see here. And that helps us in optimization of this algorithm, because we do not have to start iterating from the beginning. And then we start the backtracking process. We have a nested for loop to check each cell of the board. If we can find any children of the tries root in the board, we call backtracking with the current row, current column, and the root. And also, at the end of find words method, we return the results. Now let's see how backtracking works. As you can see, it takes three parameters: row, column, and the parent node. At the beginning, we assign the current character of the board to a character called letter. So this is the current letter that we are looking at. And then we assign the node that contains the current letter to current node. If the word of the current node is not null, for example, like here, the word of node H is oath, we add that word to the result. And then we assign null to the word section of current node, because we don't want to save duplicated words in the result array. And we also mark each cell that we visit on the board with hashtags. And that's because the question asked us to use each cell letter once. Then we set some offsets for exploring different directions. We again use the right-hand rule like the robot room cleaner problem. So we have -1, 0 for up, 0, 1 for right, 1, 0 for down, and 0, -1 for left. Then we have a for loop to explore 4 directions around each cell. So, for example, if this is the current cell that we have, we explore all of its 4 neighbors with the offsets that we have. Here we check if the column or row is out of boundary, so we do nothing and continue. But if there is any character that is equal to the current node's children, we call backtracking with the new row, new column, and current node. This condition is kind of the same to the condition that we had here. So as you can see, both of them are checking the current value in the board with the value that we have on the try. And if they are the same, we call backtracking to backtrack and find the words. At the end, we assign a letter to the cell again, and we check if the current node's children is empty. In other words, if the current node is a leaf and we have traversed it, we no longer need to traverse it again. So we prune it from try. And that gives us up to 50% better running time. Now let's submit the code in LeetCode.com and see the results. So first, let's run the code. It's been accepted, and now I submit the code. It's been accepted, and it was faster than 94% of Java submissions. Now let's talk about time and space complexity. Time complexity is something like this, which is even hard to read, let alone explaining it. But anyway, I will do my best. So M is the total number of cells that we have on the board, and as we traverse the whole board, so it is a factor in the time complexity. And here is about backtracking, because on the worst case, we assume that on each cell we can go to 4 neighbors. I mean, all 4 neighbors can lead to the word that we are searching for. So, and also I should say that L is the length of the longest word that we have on the words list. So consider that this is the first cell that I go to. So as you can see, I have 4 options to go, right? But when I go, for example, right here, so in this cell, I will have 3 options, because the fourth one is the one that I just came from, so I cannot go there. So that's why we have this. So let me write that in this way. So the first time we have 4 options, and the rest L-1 times we have just 3 options on each cell. So we have L- time, we have L-1 time 3, and 1 time 4. So that's why we have this time complexity. And also keep in mind that this time complexity is in the case that we do not use any optimization for the algorithm and for the try. It's in the worst case. But if we do some optimizations, like I said on the code section, we can improve this complexity. The space complexity is an order of n, where n is the total number of letters that we have on the board. And we assume that in the worst case, we do not have any overlapping prefixes on the try, so we have to save the try for the whole letters that we have individually. And since the try is the data structure that takes the most of our space, the space complexity would be an order of n.